Now we're going to start in on convex functions. Well, first of all, the definition is very simple. It's this. It says that a function is convex if its domain is convex, and also if it satisfies this inequality. Now, this inequality says that if I take a mixture of 2 points, so theta is between 0 and 1, if I take any mixture of 2 points x and y, convex combination, I form theta x plus 1 minus theta y, I evaluate f there, that's less than or equal to the same convex combination of the values of f, right, evaluated at the endpoints. Or another way to say it geometrically is if you have the graph of f, that's this thing, that's the graph of f, it says that the chord, some people call that's a very old term for the line segment in the graph space that goes from x f of x to y f of y. It says that the chord, and this chord here is parameterized by this point right here, it says that f lies below, the graph of f lies below its chord. So that would be the very old way to talk about convexity. A function is concave if minus f is convex. And it's called strictly convex if it is a convex function and if this inequality here holds strictly as long as theta is not 0 or 1. Well, of course, if theta is 0 or 1, it cannot hold strictly, right? But for theta in between, it holds strictly, right? So that says that there's actually a gap between the function and this chord, the function graph and the chord. Okay, so let's look at some examples. Well, we'll look first at just functions on R, just to make it simple. By the way, you can just plot these truly or virtually, and just look and use your eyeball to look at these things. And the important point here is convexity means non-negative curvature. It means it curves up. Okay, so affine. Well, an affine function, the graph looks like that. I mean, it's got zero curvature. So these are of course convex. Oh, and by the way, affine is right where you get an equals there, right? So affine says you get equals here for all theta, not just theta between 0 and 1. Okay, so in some sense, affine functions are right on the boundary of convexity. So, okay. Exponential. Well, these look either like that or like that, right? This is if a is positive, that's if a is negative. These are convex. The curvature is positive. Powers. Well, this, again, you can figure this out. If alpha is bigger than 1, this is on R+. So if it's bigger than 1, that would be a power that's like to the 1.1 or something, or 1.5. The square, you know what that looks like. The cube, these things get actually more and more convex. They curve more, they have more and more curvature. But it's also true for alpha less than 0. So for example, 1 over x is going to be also convex, right? That looks like this, right? Oh, and we should be careful here because when I say 1 over x, I have to say that the domain, if this is f, I have to say the domain is R++, right? Because, so there's a distinction between sort of informal kind of high school algebra writing 1 over x, right? And what you really mean. So usually when we say 1 over x, and we'll see this for several other functions, we mean a different function. We mean one that's not defined for x negative. Whereas, of course, 1 over x is quite well defined for x negative, right? So, okay. Oh, what can you say about 1 over x for x negative? Convex, concave? It's concave, so, okay. Powers of absolute value, I mean, again, these are kind of obvious. Negative entropy, that's something that looks like this. It's got infinitely sharp there and then goes up like that, okay? And it's convex. All right. Concave, well, affine, because they're both. In fact, affine is another way to say you're both convex and concave. Powers between 0 and 1, square root, for example, is going to be concave, and the log is a very these are very obvious concave functions. By the way, the picture here is something like this. You're going to build up a family of basic functions that you know to be convex and concave. Most will be kind of obvious, like this. Some will be less obvious. And then we're going to work out a calculus of convex functions. So you'll be able to combine them in various ways and things like that. And actually, just a couple of these things, and you'll be you'll actually be quite effective at sort of detecting convexity or establishing convexity. So, okay. Let's look at some functions on Rn. Here, a general affine function that's both convex and concave. A norm. So any norm is convex. Okay? So any norm is convex. So that's things like the 1 norm, the 2 norm, infinity norm, 3 norm, doesn't matter. Any other norm is convex. Um, and then we can look at examples on matrices. So here's an affine function. The general inner product on m by n matrices is simply trace A transpose X. So this, when you see this here, I mean, by the way, some people even write it this way, right? You can write it that way, or other people write it this way. It's basically the generic standard inner product. So when you see trace A transpose X or A transpose B, it's the inner product of A and B, right? So that's what it is. I mean, here's another method you might write this as. I find this a bit weird, but okay, something like that. I mean, this is kind of mixing weird notation, but that's it. Okay? So, all right. So an affine function of matrices is trace something and then plus a constant. Here's one, the maximum singular value. So, well, it's a norm. So, of course, all norms are convex, so maximum singular value is, right? So, by the way, that's not a simple function, the maximum singular value, right? It's quite complicated. For example, to actually evaluate it, I mean, in principle, you would form a characteristic polynomial, you'd factor that, you'd look at its roots, and you take the largest, among all the roots, you take the largest one, and then you'd take the square root of that or something. So this is not a simple function. And yet we know it's convex. Okay. So this is one of the tricks you need to know about. It's this: if you have a convex function from R on Rn into R, if you have a function, then you can restrict it to a line. Now, a line is given by x plus tv. X is something, you might call that the base point. You might call v the direction of the line. And t is a parameter, right? So t is an R, and it tells you where you are on the line. Oh, and I should say v has to be non-zero. Otherwise, it doesn't give you a line. So x plus tv, this is the, I guess, free parameter representation of a line is x plus tv, where t is a parameter that's real. Okay, so this says evaluate f at the point on the line parameterized by t, right? And I'm going to define that to be g of t. So that's a function from R to R, right? And so here's what the result is, and this is not too hard, but it says the following: a function is convex if and only if, when it's restricted to all lines, it's convex. Okay? Now, in principle, this is quite useful because let me ask this: how do you determine if a function from R to R is convex? Yeah, you plot it and you look with your eyeball. Does it curve up or down, or both, right? And if it curves up, then you say, well, it's convex. Okay? By the way, what you do then is you back off and you go to some other fancy method, like you differentiate it twice and prove some inequality. Okay? And then you destroy evidence that you actually plotted it. But the correct thing to do is to plot it. Okay? So that's how you do this. Okay? So, all right. What this says is, in principle, you can detect if a function is convex, a function on Rn, by simply taking all lines. Now, of course, you cannot really do that. But this does tell you, this gives you a perfectly good method for checking if a function is convex, and I will tell you what it is. So here's what it is. First, you might try some analytical tools. You might differentiate something twice, but after the formulas grow to the size of a page, you might quit or something like that. Then what you do is this. You write a simple little program to generate random lines, right? Then to effectively do the same as plot, just evaluate the function at 100 points along the line, and check the inequality, just to check that it always curves up. Right? By the way, if you ever find a point where it doesn't, you're done. Because you produce 2 points where the inequality defining convexity is violated. In which case, you are done, and it's absolutely no one's business how you found those points. Everyone realize? So what you do now is you go to lunch. Is everyone following this? Okay, you go to lunch, and you come back after lunch. If, in fact, it is terminated and found 2 points, then you walk down the hall to your colleague who asked whether this function is convex, and you go, obviously not. And they say, why? And you go, well, look at this point here. And you give x and y and the convex combination, which violates the inequality. And you go, I don't really even know why you would think that was convex in the first place. Everyone see what I'm saying? And then they'd say, well, how the hell did you come up with these? And you'd say, I don't know. It seems kind of obvious to me. I don't. So, okay, is everyone following this? Okay. Now, that's the other outcome is that actually it hasn't been violated. Now, you don't know for sure it's convex, But you went off for lunch and you fired this up. It depends on, maybe you used a cluster, or maybe you fired up something on EC2 or so. I don't know. But a fair number of points may have been checked by now. Now you don't know if it's convex or not. Okay? So now I can actually tell you several ways to move forward. The first is you then try to prove it's convex. That's the simplest way. And if you do prove it, you destroy all evidence that you ever tried to establish it empirically. Everybody understand this? Okay, so then, now the other thing is you can still get credit for it. Even if you can't prove it's convex, you go to the next conference and you say, well, I think the log of the detection probability, it seems to me like it's got to be concave. Stuff, and you just drop that around. You say it in obvious places and things like that. And then the next year, some smart young researcher will prove it. And if you're really lucky, they'll have attached your name to it and call it the such and such conjecture. Everyone following this? And then people would say, how did you know? The proof was like very complicated and used all sorts of algebraic geometry and all sorts of other stuff. How could you possibly have known it was concave? And then you look straight at him and you say, intuition. Is everyone following this? Okay, so these are advanced methods for establishing convexity. This is we'll talk more about these. Okay, as the course goes on. Okay, all right. So let's do one like that. By the way, if you do these things, just don't tell anyone where you learned them, because I'll deny it. So okay. So let's look at an example. Here's a very famous one. It's kind of one of the first functions. It's not obviously convex. It's log of a determinant, right? Well, that's not. By the way, these two symbols go together. It depends on what courses you've taken. But for example, you would recognize this as related to the entropy of a Gaussian random variable, where x is the covariance. I mean, so you probably have seen log determinants sitting next to each other before. Maybe, okay, but maybe you have, maybe you haven't. But the idea is that there are a lot of areas where they fit very comfortably together. And it turns out log determinant of a matrix is concave for a positive definite matrix. Just a fact. I mean, later this will be completely obvious. We'll get to it. By the way, it would be kind of a pain in the ass to show this via a direct proof. Although, if you've taken information theory and for some reason think that that's simpler than sort of basic inequalities, then you'd say, oh, that follows because entropy, some mixture or something, and you'd say something, and some theorem from information theory would tell us immediately that this is concave. Okay? Some mixture of Gauss. I don't know what it is. Anyway, okay. So let's check this, though. So how do you check it? Well, what we'll do is we'll form an arbitrary line. So what does a line in matrix space look like? In symmetric matrix space? Well, it looks like this. It's got a base point, x, and it's got a direction v. Now, x we can assume without loss of generality is positive definite, because this line has to intersect the positive definite cone. Has to, right? Otherwise, there's nothing to show, right? So it has to intersect it, and we might as well say it intersects it when t equals 0, right? So we can assume without loss of generality that x is positive definite, and then v is merely symmetric. So x plus tv is now a line of matrices. And if you want to, you can think of it as a line of potential covariance matrices. So that's what it is. It's a parameterized by t. Now, for an interval of t, for some values of t, it is possible. There's an interval where that thing is positive definite. But it is possible if you make t big enough one way or the other, it's possible, in fact, that that matrix will become not positive definite, right? So there may be an interval of little t over which x plus tv is positive definite. So these are positive definite matrices. There's a line, and it may intersect it. Now, you can have weird things where it intersects it at only one point. It's a half-open interval. But that would happen, for example, if v is positive semi-definite, the direction. Okay, so let's look at this on a line. Well, on a line, this thing is log det. I'm gonna expand. I'm gonna write this as there's several ways to do it, but I can pull out x1/2 on either side of this thing and write this I plus t. This is x minus half v x minus half and x1/2. So certainly this matrix is surely the same as that here, right? And now I take the determinant of that. It's the triple product of the determinants. And log is the sum, so I get log det. I get 1/2 log det x plus 1/2 log det x. That's this one, and this one. Okay? That's a constant and doesn't interest me as far as convexity is concerned. Now we look at this thing. So what it says is something like this. Without loss of generality, I can concentrate on the case where my base point is the identity. Okay? But log of det of I plus something, we know the eigenvalues of this matrix, right? The eigenvalues of that matrix are exactly 1 plus t lambda I, where lambda I are the eigenvalues of this matrix, right? So, and in fact, that tells you that the log determinant is the sum of log of 1 plus t lambda I. And guess what? This function is concave. And you can just check that again. My claim is that for a variable, for something with one variable, you can just check, right? That log of 1 plus t lambda depends on the sign of lambda I, which can be positive or negative. But either way, this thing is concave because log of something affine is concave, right? So that's it. So we're done. By the way, these lambda i's, they might look mysterious here, but if you had an advanced course on linear algebra, or maybe you took a mechanics course, these are actually the generalized eigenvalues of the pair xv, right? So if you're trained in these areas, this does not look mysterious at all. Okay, so there we go. By the way, this has been known about 100 years. The fact that the log determinant is concave. Okay, now there's one other thing we're going to cover is this. It turns out when you're dealing with convex or concave functions, is a very nice way that you can actually pull in the idea of the domain and define things over a bigger to have extended values. So what you could do is you take a normal function f, which has domain f, and has value when you're in the domain f of x, if x is in the domain. That's the value. So, and for an ordinary function, if I call f outside the domain, what I should get is what should be returned to me, an exception should be thrown, and the exception thrown should be a token like OOD, which means out of domain, which means I have no intention of evaluating f out there because it's not in the valid domain, right? So so you should get something like that. But you can actually modify things and do the following. What you do is f tilde is the extended value extension. What you do is it's the same as whenever x is in the domain, it's just f. But when you're outside the domain, you assign the value plus infinity. And it'll turn out everything's going to work, including like inequalities, various things. It's all going to just work automatically, right? So in some sense, it's not a whole lot different, right? And if you think of a return value of plus infinity as an exception, then, well, okay, then whether or not you get the exception OOD for out of domain or plus infinity, I guess doesn't matter much. But what's nice about it is if you think of it not as an exception, but as an extended value, all sorts of inequalities and things like that will just work, right? So this is the extended value extension. And it simplifies notation, right? So for example, this holds now for any x and y. You can sort of just check. And there's a couple of rules. There are a few things that are not well defined in extended arithmetic. Obviously, well, 0 times infinity is not well defined. But everything else is. The inequalities, everything. Everything's well defined here and just works. Okay, so this is the extended value extension. This will also come up a bunch of times. Okay, now we get to sort of first order conditions for convexity. Well, if f is differentiable, right, that means its domain is open and it has a gradient. These partial derivatives exist at each point. Okay? Then, by the way, this constructor here, which is a parentheses here with a list in the middle, is actually a column vector. So that's the standard notation. It's more compact, right? So this is a column vector, and it actually looks like this, right? Like that. That's the same as that. And the first order condition is actually extremely interesting. It's one of the most important things, and actually it's kind of the one thing which kind of tells you everything. It's this. This function here, that is the first order Taylor expansion of f at the point x, right? So y is the variable here. That's an affine function of y. This this thing. It's an affine function of y. It's the first order Taylor expansion of f at x. Okay? So if this is f, right, here is this first order Taylor expansion. That's this function here as a function of y. Okay? And here's what calculus tells you is the following. This function is really close to f if you are close to x. It means that if you're close to x, this function is close squared to f. That's what calculus tells you, right? That's the whole thing. What this says, instead, the assertion here is a global inequality. It basically says the function is bigger everywhere, globally, than the first order Taylor series expansion, right? And so this is your first hint that what you are seeing is not calculus. It's some weird, sick, global, and asymmetric thing. We have a different animal here. The first thing is it is an inequality, right? That's the first difference with calculus. Calculus is just, above, below. You only have the concept of close. And it's symmetric. You can be above, below, you're close, right? And it's weird and local and asymptotic. There are no conditions here. This is just, it's a global inequality. Just looks like that. Okay? So that's it. So this is actually very important. Actually, this is also going to come up later in the class. You're going to be doing convex optimization. You'll be solving, I don't know, some problem with 1,000 variables. I don't know. And someone will come along and say, what are you doing? I'm solving this problem. And you'd say, here's the solution. And they'd say, oh, well, how do you know that's the solution? You go, oh, no, it is. No one can do better. But R1000 is a giant place, right? That's a huge thing. You can't possibly go to lunch and check other points and come back later and say, I checked 1,000,000 points, in R1000. That's like zero. Okay, so you know nothing. That is all I'm saying. So someone could reasonably say, how do you know? How could you possibly assert that this is the best, that no one can do any better in such a giant place? And the answer will be this inequality here. That's it. Because the whole thing is constructed on the basis of global asymmetric. Well, asymmetric is an inequality. That's what it is. Okay, second order conditions. Well, if a function is twice differentiable, that means it's got all these partial derivatives exist, and that's denoted the Hessian, so sometimes written this way, right, of the function at that point. And what it says is the following: if f, it says that f is convex if and only if its second derivative is non-negative. Now that's a matrix, so that means positive semi-definite. Okay, so that's the condition. Now it turns out there's a weird asymmetry here. If the second derivative or Hessian is positive definite, that's not enough to guarantee. That guarantees strict convexity, but the other way around is actually false. You can be strictly convex without having the Hessian positive for all points in the domain. Okay, so there are things you can say about that, but that's good enough. So that's it. So that's another way to say it is, again, the second order expansion. When you get that second term is, in fact, the matrix is positive semi-definite. Okay, so let's look at some examples. Let's knock off all quadratic functions. Here's a quadratic function. Without loss of generality, we can assume that P here is positive semi-definite. Symmetric, right? Because otherwise you get the same quadratic form. The gradient of this function is px plus q, right? And the Hessian is p. Okay, so that's the Hessian, and then it's really simple. A quadratic function is convex if and only if its quadratic part is positive semi-definite. Okay, so here's an example. Is least squares objective? So let's take f of x as ax minus b norm squared. Well, the gradient is, and you can put a 1/2 there, for aesthetics, or it doesn't make any difference, and people often do just for aesthetics. The aesthetics is the following: that you don't get this 2 and you don't get this 2, right? So, the gradient is A transpose AX minus B, and the Hessian is simply its constant. It's A transpose A. That's always positive semi-definite, so you're done. Okay? And here is, I think, probably the simplest function. Well, we've already seen log det. That wasn't obvious. But this is sort of a really simple function. And it's the first one most people don't know is convex. It's a really simple function. It's x squared over y. And it's a function of two variables, x and y. And the domain is y has to be positive. Okay? And here's a plot of it. So there's the plot. By the way, you've seen that plot actually twice before, I claim, weirdly. The first is, you saw it when I gave you a plot of the positive semi-definite cone in two variables, right? And I think I mumbled something incoherently about somebody telling me once this looks like the front of a ship. Okay? I also said that if you took that thing and rotated it, it's actually the same as the Lorentz cone. It's the cone, right? So there's a lot of mileage from one stupid cone, right? It's come up 3 times. But the point is, it's the graph of x squared over y is this thing. And it turns out now, you can verify many things, but you just work out what the Hessian is. I mean, this is kind of high school calculus. You work out what the Hessian is, and sure enough, the Hessian has this form. It's rank 1, but it's positive semi-definite. Okay? And you get that. So that tells you, and in fact, it even tells you a lot, the fact that it's rank 1. The fact that it's rank 1 tells you that at any point on that surface, it's sort of curving in one direction, but not the other. Right, so that's what it says. In one direction it's flat, in the other direction it's got positive curvature. Okay, so x squared over y is convex. By the way, we're going to see lots of implications of this, right? This is going to come up in like robust statistics and all sorts of other things. It's going to come up a lot. You'll see. Okay, here's one. It's log sum exp. And what it is you take the log of the sum of a bunch of exponentials. And before we get into it, I want to give you a rough idea of what this function is, because it's going to play a big role in a bunch of stuff you probably have seen before, will see again if you're taking the right courses anyway, and we'll see also in this course. So here's what log sum exp is. So first of all, it's the power combining formula in electrical engineering in decibels, right? So again, so this is, I'm going to go into dialect. So those of you not in electrical engineering, I apologize formally, but that's okay. So I'll go into dialect. So if I tell you that you have a bunch of signals coming in, you know, one at plus 5 dBm, one at minus 12, one at this or whatever, something, and I say what's the total power incident there, what you would do is each of these are decibels for the rest of you who don't speak this dialect, is a log of a power level, right? So if you want to convert these to powers, you form an exp. I mean, there's some, you know, factors in there, but I don't care about them. So you form an exp. Then you add the powers. Now we're at the sum exp. We're up to here, right? And then the log reconverts back to decibels. Okay? So my claim is that everyone in EE knows this. It's the dB combining formula. So don't pretend like you haven't seen it. You have seen it if you're in EE. The second thing is this is a smooth approximation of a maximum. Okay, and in fact, another name for this function is softmax. Okay, so that's that, and that you may have seen in, I don't know, maybe a machine learning course, maybe something like that. It's a soft, is that what it's called in a machine learning course, softmax? Okay, good. And the intuition is really simple. It says this: if I got a bunch of numbers and I take the exponential is going to actually accentuate large numbers. Like if 1 or 2 numbers are much bigger than the others, their exps are much bigger than the exponentials of the others, right? You add them up, and the big ones dominate. You take the log, and you get something. So it's like a soft approximation of the max, right? So that's another name for the softmax. And it's also a normalizing function in statistical mechanics for something. And it comes up in lots of other things too, but maybe not quite with this notation. Okay. So this is convex. And again, the way to show that is to work out the Hessian and then to write it this way. Now, unfortunately, the proof was either going to be shorter or a bit longer. It's not totally simple because this one is positive semi-definite, clearly. Unfortunately, that goes the wrong way. It's minus, right? So you actually have to do some work to show this is positive semi-definite. And to do that, you really have to show that this thing here is positive semi-definite. So you form something like V transpose times the Hessian times V, and you argue that that thing is bigger than or equal to 0 for all V. And you might do that this way. You might use Cauchy-Schwarz, right? So Cauchy-Schwarz would tell you this inequality, right? That would be the Cauchy-Schwarz inequality applied to square root zk and square root zk vk, right? The two vectors. You apply Cauchy-Schwarz and you get exactly this, right? And that tells you up here that this thing is bigger than or equal to 0. So by the way, I'm not going to go into. You're not supposed to be getting this in real time. You have to go off to a quiet place, check that you believe all these things, and so on. So okay. Geometric mean. So the nth root of the product of a bunch of positive numbers, well, or non-negative for that matter, that's concave. And it's the same kind of thing. In fact, it turns out that for a function like that, and for many functions like this, it turns out that the Hessian is non-negative diagonal minus rank 1. That's what this is. And you get the same type of argument holds. Okay. So what's the connection between convex sets and convex functions? And that's this. It's through a simple thing called the epigraph. So we'll encounter a whole bunch of things. One relating sets and functions. So here's one. If I have a function, then its alpha sublevel set is this. It's a set of points in the domain, although, of course, if you use extended value, that happens automatically, where f is less than alpha. Okay? So that's the sublevel set. Right? And by the way, this will have all sorts of practical meanings when we get into this. For example, if f is an objective that you want to minimize, then the alpha sublevel set are the set of points or designs or choices or whatever the x represents, which are at least as good as alpha. They're the alpha good or better points, right? So, and if you have a convex function, the sublevel sets are convex, okay? So the set of points better than something, if you're trying to minimize it, that's convex, okay? The converse is false. You can have convex sublevel sets, and you're not a convex function. And in fact, those functions have a name. We'll get to them later. The closest connection, the correct connection, is through something called the epigraph. So epi means sort of above, and graph means, of course, something that's drawn, or in mathematics, it's the pairs points comma values in Rn plus 1. In graph space, people call Rn plus 1. And so the epigraph of a function, it's the set of all pairs xt where f of x is less than or equal to t, right? So the normal graph is equals to t because you just get the surface of the function. The epigraph is everything above it, right? So it's this shaded thing here. It's the epigraph. Okay? And here's the connection. Very simple. So a function f is convex if and only if its epigraph is a convex set. And that's the connection. So the real connection between convex functions and convex sets is through the epigraph, right? And in fact, we'll see all sorts of cool things. You know various things about convex sets. Those will all translate to various rules about convex functions. And we'll look at a couple of those and all that kind of stuff. And so in fact, what it will really mean is that moving after a while, when you start internalizing all these, you'll have different ways to say the same thing. One will be there'll be a statement about sets, there'll be a statement about functions, and the connection will be through the epigraph. Okay. So Jensen's inequality, it's about 100 years old. Now maybe actually a little bit more. Actually, the inequality was around earlier, obviously for very specific things. And it was Jensen who kind of looked at it and said, hey, you know what? Everyone keeps keeps talking about the same inequality, and here's what it is that they're saying. So that he just collected the name for it. Okay. Basic inequality says this. If f is convex and you have theta between 0 and 1, you have that. Now, in fact, that's the definition of convexity. So I don't know. Anyway, that's called Jensen's inequality. Okay? Now, it turns out Jensen's inequality, you can generalize various ways. Number one, to finite sums, right? So if I have a set of points x1 through xk, theta 1 through theta k, theta I non-negative, add up to 1, f of some theta I xi is less than or equal to some theta I f of xi. Okay? So that's it. Then you can extend it to infinite sums, integrals, and finally you go all the way and it's just expectations. So the right way to say it is this. If you have a random variable z that takes values in the domain of f, right? By the way, if it doesn't take values, if there's a positive probability it takes values outside the domain of f, then there's really not much to say here. But so it takes, its values are in the domain of f almost surely. Then the following is true. F of the expected value is less than the expected value of f of x. That's it. And guess what? This very basic inequality here is exactly this is the most general form of the inequality. And this is a special case of that for a very specific distribution on z. I mean, it's really dumb. It's atomic. It's a distribution that has the value x with probability theta and probability y with probability 1, has the value y with probability 1 minus theta. Then this is a special case of that. So this is another way to talk about convexity. It's a function is convex if it doesn't commute with expectation. That's affine, right? But what it does is expectation always, I mean, there's lots of ways to say this, but, well, when you commute them, you get an inequality, right? So actually, one way to say this is, and this is weird, and this is a little bit dialect, but dithering increases the value of a function, okay? That the dithering is to add noise to something, zero mean noise to something intentionally. Okay, so now let's talk about some of these operations that preserve convexity. So what you will be doing will be establishing convexity of functions and sets for that matter. And so how do you do this? Well, one is just every now and then, although quite rarely, the best thing to do is just roll up your sleeves, pull out x, y, take a theta between 0 and 1, and just jump in, and then establish an inequality. That's actually extremely rarely is that the right thing to do, right? But it is sometimes. Or you could restrict to a line and verify it. That's another option. Now, for twice differentiable functions, you can differentiate twice. And if the function is simple enough, go ahead. If it's not simple, and in fact, it takes very little before this method is completely unworkable, just because the notation proliferates and you get horrible expressions, and you write it down and there's half a page of stuff, and someone says, what's that? And you go, that's partial squared f, partial xi, partial xj, and then they say, what do you have to do now? And you go, prove that half page of formula represents a positive semi-definite matrix, right? And this is not fun. So now I think a more modern way to do this, certainly a way that is more useful, and it's the way you will do it in this course mostly, is the following, is you'll actually do this constructively by a calculus. And what that means is you'll know a bunch of convex and concave functions. You've already seen a bunch, norms and square root, log, entropy, geometric mean, all sorts of things like this, right? You'll have those. You'll have, and that by the way, that list of atoms will grow as you learn more of them. And then you'll have some operations that preserve convexity, right? So some of them are going to be totally obvious and stupid, like the sum of two convex functions is convex. Well, duh. 2 times a convex function is convex. Fine, right? -3 times a convex function is concave. Okay, fine. Others are going to be way less obvious, okay? So we'll get to those. And it turns out you don't have to know a whole lot of these things before you put them all together, and you're actually quite powerful at establishing convexity or concavity or something like that. And that's going to be the thing. Or if you like to think of it from a computer science point of view, your proofs or verifications of convexity are going to look like this. You're going to have expression trees. The leaves are going to be things you know are convex or concave. That's what's going to happen. And all of the internal nodes in that expression tree are going to be expressions whose convexity or concavity you can tag by one of these calculus rules. So if you understood that, great. If you didn't, you will, because we're going to force you to. All right, so let's start with the obvious ones. I mean, positive weighted sum and composition with an affine function. So non-negative multiple, I mean, these are kind of obvious. By the way, these things do have to be shown, right? So somebody should show them, or you should show them, or something like that. I'm certainly not going to do it here. Sum, right? So if you add two convex functions, it's convex. I mean, it's kind of obvious. Composition with an affine function. If you precompose a convex function with an affine function, the result is convex, right? Same for concave. Let's look at some. Here's one. Log barrier for linear inequalities. So here's a function. It's the sum of minus log bi minus ai transpose x. The domain is this open polyhedron. It's the set of points where it's the interior of this, right? So it doesn't include the boundary, is what the domain of f is. And in there, we can even interpret these terms. That's the margin in the ith inequality. If you require bi to be bigger than ai transpose x, strictly bigger, that's the margin. It's a positive number. You take the log of that. Well, okay, that's if the margin is small, that's a very large negative number, and the minus sign converts it that way. So it turns out this is a convex function. It's called the logarithmic barrier function for this polyhedron, and we're going to see a lot of that later in the class. And you can guess kind of why it's called a logarithmic barrier, because if you were to visualize that function on this polyhedron, this function, it goes to plus infinity on the boundaries, right? As you move towards a boundary, one of your margins, at least one of your margins, gets really small. One term in here goes to 0. the log goes to minus infinity, and the minus makes it go to plus infinity. So it's like a barrier. If you think, like in physics, a potential function, it's an infinite potential well. Okay, so that's what this is. All right, you can have the norm of an affine function, right? Because that's an affine function composed with a norm, which is convex. And I mean, this is kind of obvious, but we'll quickly get to ones that are not. So pointwise maximum. So if you have a bunch of convex functions, then their pointwise maximum is convex. I mean, this is kind of obvious. I'm just going to draw a picture. Here's one function. Here's another. Here's the pointwise maximum, is this function here. That's the pointwise maximum, and it's convex. I mean, the picture is clear. It's 2 lines of a proof. If you can stretch it to 2 lines, you know, it's not hard to show. Actually, this is very interesting, and this tells you that you are not in the calculus mode anymore. Here's why. This is one of the most basic constructors of convex functions is through pointwise maximum. And what's completely clear, even this little example I just drew, is it does not preserve differentiability. Right? Max of even differentiable functions is generally not differentiable. Okay? You get points. And in fact, that's kind of a theme for the whole course. It turns out differentiability doesn't play a huge role in convexity, or certainly in convex optimization, it doesn't play a big role. So again, these are just things that you're going to, this will be clear, but this is kind of your first hint that this is not going to be like a calculus class. So here are some quick examples. Piecewise linear functions. So the maximum, if I have a bunch of affine functions, then piecewise linear functions, just a maximum of them, that's convex immediately, right? So, by the way, that's a very specific form of a piecewise linear function, right? Because normally when people talk about piecewise linear functions, they talk, you specify the little regions, and then on that region you say it has this value and this value and so on. This one kind of does all that implicitly. It just says it's the maximum of a bunch of functions, right? Here's an affine function, here's that. That is the maximum. The function that looks like this, that's a piecewise linear convex function, right? And it's just the maximum of a bunch of affine functions. Here's one that's less obvious. How about this? The sum of the r largest components of a vector. Okay? So the sum of the 5 largest components. That's kind of a complicated thing, right? If anything, you should be getting a combinatorial feel for it. This is convex, and the argument is really quick. Let's talk about different ways you might show this. Okay, let's talk about differentiating. Let's talk about it. So what's the derivative? What's the gradient of the function which is the sum of the 5 largest entries in a vector? Wherever the 5 largest elements are bigger than, there's a gap between the 5th and 6th element in the vector, that function is actually just affine. And what is the gradient there? It's a vector with a 1 in each component if you're among the top 5 and 0 otherwise, right? So that's fine, it's got a gradient. And you could try to show that gradient inequality or something like that, ignoring the fact that in fact the gradient doesn't exist when there's a tie between the 5th and 6th elements in this function. And the Hessian, it's just 0 everywhere except on these points where it doesn't exist and all that kind of stuff, so it gets weird. Okay, so that doesn't work. But it's actually very easy to say what it is. It's a maximum over n choose r linear functions. Because what I do is this. I simply say, I take all vectors which consist of r1s and n minus r zeros, and of which there's n choose r. Right? So I take all those vectors and I take the linear function, which is that vector inner product with x. That's the sum of a particular, actually each one of those inner products is the sum of 5 particular elements. I'm going to take r equals 5. So it's the sum of 5 particular elements in that vector, right? And now I take the maximum of all of those, right? That will give me the sum of the 5 largest. Okay? So there's a 2-line proof, 1 line, that the sum of the 3 largest entries in a vector is convex. Okay? So that's it. By the way, this doesn't give you a good way to calculate it this way, but still. Okay. Well, this idea extends actually to infinite sums. And it's the same way, if you go back to the epigraphs, it's the same way it says that intersection of an arbitrary number of convex sets is convex. So here, pointwise supremum is you can have the supremum over an arbitrary set of functions, right? Arbitrary set of convex functions. So the idea is this. If you have a function, f of x and y, y actually can be completely abstract. It does not have to be a vector in Rn, right? It could be indexed by sick things or strings or weird, I don't know, anything, right? Doesn't matter. It says that if this function is convex in x for each y, then the supremum of these functions is convex in x. And we can look at some simple examples. Here's one. The support function of a set is this. Here's a set. Here's a set. It doesn't have to be convex, right? Like that. That's C. And the support function says, here's a vector y. You actually form the largest inner product, and so that would tell you, well, I didn't draw it right, but it looks something like that here. I'll bend my set to touch it there. Okay? So this would give you, it tells you how far you can go in the direction y, and it's as a function of y. That is a convex function of x. Okay? And so let's see, why is that? Why would you say that? Well, what kind of function of x is y transpose x? It's linear. Okay? So it's linear, therefore it's convex, because convex promotes to linear, right? I'm sorry, linear promotes to convex. Okay? So, and then it's a supremum over them, so that's convex. Here's another one for fun, is the maximum eigenvalue of a symmetric matrix, right? That's one way to write that is this. It's the supremum of y transpose capital X y subject to norm y equals 1. Okay, the answer is the maximum eigenvalue of x, right? That's almost the definition. Okay, so then the question is, how do we know that's a convex function? By the way, we already talked about it. It's a quite complicated function, right? It involves writing out the characteristic polynomial of x, factoring it, taking the largest, all this kind of stuff. So let's see. What kind of function of capital X is y transpose x y? It's linear. And that's right. Actually, this is the first time you've seen this. There are going to be lots of times. When someone walks up to you and you see y transpose x y, the quadratic part of your brain is already sort of activated, right? Because y transpose x y is quadratic, right? So, but here you have to think very straight, because someone says y is given, x is the variable, and that thing is linear, right? So this is kind of the idea. And then we take a supremum of this over all possible y, and you get something that's convex. It's composition of functions. So here's the idea. I have a function h, and I have a function g, and I compose them. So I take h of g of x, I'm going to call that f. And the basic rule is very simple. It turns out that a convex increasing function of a convex function is convex. Okay, so that's the basic composition rule, convex increasing. Now there's some details here, and they are actually important. They are not little sort of analytical things that only a mathematician would worry about. They are quite real, and they have all sorts of consequences. The first is this: the outer function here, the one that you apply, the increasing or non-decreasing restriction there is actually on its extended value extension, right? So here, h tilde is the extended valued extension of h, okay? And so what this says, and we can look at some examples. So here's a function. Let's take h of x equals x squared with dome h equals r plus, okay? Now, in fact, you would normally say that function is non-decreasing, it's increasing. It is increasing. If you take any 2 points on its domain, which is not non-negative numbers, one is bigger than the other, then it's bigger, because a square makes things bigger, okay, period. So that's an increasing function. That's not good here. That won't work here, because h tilde looks like this. H tilde, I'm just going to draw it kind of as a diagram. It kind of goes up here to plus infinity, okay? And so the point is, that is not an increasing function. Well, in fact, you can see it goes from plus infinity down to 0. And in fact, if I compose this function here with something like x minus 1 squared, actually the conclusion is wrong. You get a function that is not convex. Okay, so these are details, but they're actually important ones. I don't expect you to get it here. You should be you'll read this part of the chapter. You'll do homework exercises and things like that. Then it'll become clear. But the 0th level one that you should remember is convex increasing function of a convex function is convex. Okay, so and then there's variations on that. You have a function is convex if the inner function is concave, but h is instead of non-decreasing, non-increasing. So it's basically a decreasing function. Okay, informally. So that's the idea. Now, how do you prove this? You can actually prove this directly, and it's actually quite simple. And in fact, it's even clearer because a basic proof of this one in the book, basically does not require, it makes no assumptions whatsoever about h and g. They don't have to be differentiable, nothing, right? But an instructive proof is actually to do one assuming that these are scalar that x is scalar, and that these functions are differentiable twice, right? So in that case, you just take the chain rule and you work out what the second derivative of f is, right? Because essentially convexity is a statement about the second derivative, right? When a function is convex, or sorry, when a function is smooth. So here, you simply work out what the second derivative here, and you get this expression here. And so this composition theorem here is actually going to turn out to be very simple. It's a case where trivially you can assert the sign of the second derivative. Okay, so let's look at it. If you look at the first term, you see that there's an h prime prime. So let's look at this theorem that says that a convex increasing function of a convex function is convex. Well, here h prime prime, that's this thing is bigger than or equal to 0. That's what it means to be convex. This is squared, and so it's totally irrelevant. It's non-negative, right? Then this thing here, that's the assumption. It's of a convex function, so this is going to be non-negative. And then this here, now you can see where the monotonicity requirement comes in. The monotonicity requirement comes in because it gets multiplied by h prime, right? So another way to say it is something like this. So this will be very rough, but this composition theorem tells you when you can deduce the sign of the second derivative using, well, calculus, and then a very elementary sign arithmetic. Sign arithmetic is very simple, right? It means you multiply two things that are non-negative, you get something non-negative. You add non-negative things that are non-negative. You add you multiply a negative and a positive thing, you get something negative. That's like sign arithmetic. Okay, so it says that basically from calculus and signed arithmetic, you can conclude the sign of the second derivative. If it's positive, you got a convex function. If it's negative, you got a concave. Everyone following this? Okay. So, but the funny part is actually the proof that holds completely generally, right? Not for differentiable is actually easier than this. Well, at least mathematically, it's easier, right? All right. So what are some examples? It says that the exponential of a convex function is convex. Okay. And the inverse of a function is convex if the function is concave and positive, right? So 1 over a concave function is going to be convex, right? So, okay. All right. Now, there's a vector version of this, right? When a function takes multiple arguments. And actually, this is incredibly important. We could argue that the one thing on this page you're going to use probably every day for the rest of the quarter. Maybe not today, tomorrow, but starting like next week, I promise you, you will use this every single day. So, or we're going to arrange the homework load to ensure that you will be using this every day. So this is it. Here it is. It's this. It says, so all I'm saying is this is going to be a big part of your life is going to be actually just this one composition theorem. It's this. It says, suppose you have a function, so g of x is rk valued, right? So I have a function h of k arguments, g1 through gk. And I want to conclude convexity of that thing. Well, a simple one is if the enclosing function h is convex, and then there's a rule, and it says that for each argument, these are the two simple versions, but then I'll give you a completely general version. The simple version is this, is that if each of these arguments is convex, right, and h is increasing in each argument, okay? And in fact, it's h tilde, the extended value extension, but that's the idea. So in fact, it's the natural extension, right? So what it says is this, right? Each of these, right here, H is you analyze the monotonicity with respect to each argument, and if it's increasing in every argument, then you can take a convex function at each point. Actually, you can mix and match these. So let me explain that. And in fact, let me give you a very general one. It goes something like this. F is convex if, and this is only sufficient, it is absolutely not necessary, it's if the following is true. For each I, right? And I'll give you a more general version, and we'll have an exercise on this, so don't worry about it, but I just thought I'd say it now. One of the following occurs. First, if GI is affine, then there are absolutely no monotonicity requirements on the enclosing function H, right? That's the first one, right? Or GI is convex and H is increasing in arg I, okay? I'm writing this informally, but you know what I mean. Or GI is concave and H is decreasing in arg I, okay? So that's it. So now, one of the reasons that you need to know this is because this is the basis of, for example, CVX, which you'll be using starting next week, okay, which is a software system for doing convex optimization, convex analysis, things like that. And it's all based on these basic rules of convex analysis, right? Although they're basic, but you get a lot out of them. So this is the idea. There are details here like the monotonicity has to be with respect to the extended value extension. So you have to take the domain into account. So this is a generalization of the others. Actually, here's a very interesting fact. All the other rules you've seen so far, almost all of them, this includes them, right? When you teach this stuff to humans, you say things like, look, it's good to know that the sum of convex functions is convex, right? That follows actually from this directly. Because all I do is I take H, the outer function, to be the sum. It's kind of a silly, right? It takes two arguments and it adds them, right? So that's a convex function. I mean, sure, right? It's convex. Oh, and guess what? It's monotone increasing in each argument. Therefore, the sum of two convex functions is convex. Now, that's kind of pedantic, right? Because you're using a sledgehammer to show something that's quite obvious. Everyone following this? But my point is that, in fact, this is kind of the only thing you need to know, actually. Is just this one thing. Here's max. We looked at that. We said that we observed that the max of a pointwise max of a bunch of convex functions is convex. Well, guess what? All you do is you take this theorem, you take H is the max. That's a convex function by itself. It is increasing in each argument. It's non-decreasing. Right? So, you have to distinguish between informal speech and then when you're writing. So when I'm talking, it's informal speech, and I say increasing to mean non-decreasing. Okay, so this also tells you that the maximum of a bunch of convex functions is maximum, pointwise maximum. So you actually get a lot out of this one composition theorem. So let's look at an example. You have something like this. Well, let's see. The sum of the log of a bunch of concave functions is going to be concave, right? And that would follow from something like this. Here's one. Log sum exp of gi of x. If the gi's are convex, log sum exp gi, that's convex. By the way, you should be getting a little bit of let's talk about that a little bit, and I'll just say a little bit about it. Log sum exp you should think of as a soft max. It's an analytic or smooth approximation of the max function. But the max of a bunch of convex functions is convex. So intuition suggests that log sum exp would be convex. So immediately we get this is consistent just by intuition, right? And then, now there's all sorts of things we could do here to parse this and establish convexity. I'll show you one that doesn't work first. The first one is to simply parse it from the inside and go out. Here's one. What can you say, if GI is convex, what can you say about exp GI? It's convex, because that's the most basic thing there is, right? It's convex increasing function of convex. Okay, how about the sum? You can label that. It's convex. Okay, how about the log of a convex function? Right there, in fact, it's false. There's no rule you can have the log of a convex function. It's nothing. It could be that can be concave. It can be convex. It can be anything. There is no rule that says the log of a convex function is anything, because it just isn't one. Everybody see that? So that failed completely. What is the correct parsing of this? What you do is you make h the log sum exp function. The log sum exp function is clearly what's convex, and it is increasing in each argument. By the way, there it really is increasing, so I'm okay. That's informal and formal. And therefore, log sum exp of a bunch of convex functions is convex. Everybody got that? So actually, a lot of this will become much clearer as you get into actually doing these things. But what this says is, proving convexity of something, it's not as, you just don't write the first parse tree that comes down because it might be wrong. The first parsing might, well, sorry, not that it's wrong, it won't work using these rules. Okay? Okay. So minimization is a very general construction. Oh, and I should contrast this with maximization. You'll remember the following, that if I had a function f of two variables here, if this function is convex in x for each y, then the following is, this is just y in any set, right? This function is convex in x, right? So there's absolutely no requirement that the function be convex in x and y. And in fact, y here doesn't even have to be a vector. It could be some, any other kind of, it could be some weird combinatorial thing. It could be over parse trees, or it doesn't really matter. It could be anything, right? So the supremum of an arbitrary family of convex functions is convex. What's interesting is infimum, the minimum of a convex function, sometimes yields a convex function, but it's in very specific cases, and the conditions are stronger. It's this. If you have a function that is, it has to be jointly convex in x and y. So it's convex in both x and y. And if you have a convex set, then the infimum, this is sometimes called the partial minimization of f, right? Because I have a function f of two blocks of variables, x and y, and I'm going to minimize it over one block, and that will leave a function of the remaining variable. Everybody got this? So that's called partial minimization, is another name for this operation, partial minimization. And partial minimization here preserves convexity. So if you do partial minimization, you get a convex function. This is actually extremely important. This is kind of the basis of a lot of things like dynamic programming or something like that. It says that you can minimize over some things and look at this as a function of what's left. And then you can minimize over some more things and some more and some more and some more. And that would give you dynamic programming in the right circumstances, right? So that's the idea. So this is actually quite important. Okay, so this is called partial minimization. And it comes up in a whole bunch of things. You'll see some of it later, surely. Oh, by the way, in terms of epigraphs, this is embarrassing. Look here, it looks very complicated. Like, oh my God, you're minimizing this thing, and it's complicated. It turns out, in terms of epigraphs, this is nothing but projection. This is a projection of an epigraph onto the first, whatever it is, n components. It's nothing more. You can check that, right? Okay, so here's a very famous example. Let's take a quadratic function. So that's it. But we're going to block the variable into the argument into two parts, x and y, right? So here's a general, that's a general convex quadratic function of two sets of variables, quadratic form, x and y. And what we're going to do is, and it is jointly convex in x and y. That means this block matrix is positive semi-definite. For simplicity, we'll assume C is positive definite. You actually don't need to, but that's okay. And now, if we minimize over y, you can do that analytically. You just set the gradient equal to 0 and various other things. And what you'll get is the result is actually a quadratic form over x. And the matrix there is this thing. It's A minus B, C inverse B transpose. You probably have seen this matrix before. If not, get used to it, because you will see it in pretty much any class you take, any good class. If you don't see it, then I'm suspicious of the class. Right. So, for example, this is the matrix that comes up for example, in circuits analysis, in mechanical engineering. Everything is this, right? Analysis of structures. In probability, this is conditioning. This is the covariant. This is the conditional covariance. This is how you condition, right? So, and it's actually a nice thing to remember in your head as a big high-level thing. Is quadratic functions actually are preserved under partial minimization. That's actually extremely important, right? It says that if you take a quadratic function, convex quadratic function, and you minimize over some variables, then the result is a quadratic form, convex quadratic form in the remaining variables. And in fact, specifically, it's the Schur complement. This matrix is called the Schur complement. So, okay. And we'll certainly have an exercise on that. And you're going to encounter the Schur complement like throughout the class. And for that matter, throughout every other class you take, I hope. Another not obvious operation that preserves convexity is perspective mapping. So perspective mapping is this, and you'll remember the perspective, the projective mapping for convex sets, right? That was something that took x and divided by the last component or something, and it basically it's what it looks like when you see a three-dimensional object when you put that onto an image plane, right? So this is the perspective of a function is this. You have a function from Rn to R. The perspective is a function on the graph space. So it actually takes two arguments, one in Rn and one in R. In fact, R plus, actually R plus plus, so positive argument. And it's this, it's Tf of x over t. So that is the perspective of a function. And it is the domain is the set of points where t is positive and x over t is in the domain of f. And it turns out this is jointly convex in x and t. Okay, so that's the, and by the way, very simple, if you want to know what does this look like in terms of epigraphs, this is you have the projective transformation on the epigraph. And so that's what it does, gives you this. So let's look at some examples. Here's one. Well, let's see. F of x equals x transpose x, that's the sum of the squares. That's convex. In fact, in some ways, that's your canonical smooth convex function, right? The graph is a bowl. That couldn't get simpler than that. So if you calculate the perspective of that, it's this. You take, well, basically you take t and then x over t transpose x over t. And when all the smoke clears, you get the sum of the squares divided by t, and that's convex, right? So now you remember we showed x squared over y was convex when y is positive before. And that's got various names like, quadratic over linear, I don't know. There's lots of names for that function. But we did it by calculating a Hessian, which was fine. It doesn't kill you to calculate a Hessian. But here it says that this follows instantly from the perspective mapping, right? Here's one. The negative logarithm is convex. So if I calculate what its perspective is, it's simply t log x over t. And that is this thing. And it says that's the relative entropy. And it says that is going to be convex on jointly in t and x, right? So a lot of things will come out. You take an innocent function where convexity is obvious or concavity like log, and you apply something like this, and all of a sudden things like Kullback-Leibler divergence comes out. Functions that look like it would actually be kind of a pain in the ass to prove are convex, and they just pop right out from this rule. Okay, so they also often have interesting meanings in that field. So if you're in a field and you work out the perspective of a function, right, it often has some interesting meaning in that field. So, okay. The conjugate. So this is also something that's going to come up like crazy in Chapter 5. And this may have come up in other classes you've seen, especially if you took economics, except it wasn't stated this clearly, unless you took a graduate course. But if you took an undergraduate course, you saw this, but they went on and it wasn't clear. But anyway, so the conjugate of a function is this. And again, all of this is sort of without context. So starting next week, beginning of next week, you'll actually start seeing applications and stuff like that. But for now, all of this is without context. So here's the conjugate. The conjugate of a function is this. It's denoted f star here. And I mean, that's kind of standard, right? Because there's a whole bunch of mathematical terms that you use, and they kind of evoke the same thing. Dual, conjugate. Can you think of any others? Adjoint kind of thing. These things. And what they all suggest, things that if you do them twice, you get back to where you started or something like that, if certain things happen, right? So this is the conjugate. It's one of them. Transpose would be another word like that. So here it is. It's the supremum or the maximum of y transpose x minus f of x, right? So that's what it is, right? So and you know there are a lot, you can give lots of interpretations to this, beautiful interpretations, in fact, right? Like let's see, you could do something like this. This could be something like this. F of x is a cost. If x is a set of vectors, it's a vector that tells you how much of, let's say, some commodities that you own, right? F of x tells you your cost. I guess economists make it, they look at minus f of x, that's your utility, right? So we look at f of x. F of x is your cost, and that's how much it irritates you to own that amount. I mean, if it's negative, I suppose that means you're happy or something like that. But anyway, so that's f of x. Then y here has the interpretation of prices. So y is a price vector. And then what you're saying is the following. It says, if the prices were y, how much would you, of each of these things how much would you purchase? And the answer is, you would take your f of x, that's how irritated you are, and maybe I got the sign wrong slightly or something here. Maybe minus y is the price vector. But I would take f of x, and to that I would add how much I have to pay for it, and then I'd minimize that, and that would give me the amount I should buy, so that the sum of how irritated I am plus how much I had to pay for the goods is minimized, right? And so that's where things like this come up, and it comes up in lots of other fields too. So, and we'll see things like this. So, okay. So the picture is something like this. Here's your function, and then what it says is to evaluate the conjugate, what you do is you take a slope like y. So we're going to evaluate it at y, and we take a slope like that, xy. And then it says we're going to maximize the difference between this thing and f of x, right? And so that means you move this way until you just touch here. And then, in fact, if you simply move over here, that gives you the height of this is the negative conjugate here. So in fact, in this case, for this example, we could even do things like I could ask you questions about what happens if I increase y. So, for example, let me do this. For this example here, if I were to, y is maybe about 1 here, and I would like to know if I make y 2, what happens to the what does the negative conjugate function do? Just visually. Well, what happens? It goes down. Yeah, the negative conjugate goes down. So what happens is the slope is now 2, and your point of tangency might be like here, and then it might go down right down to there, right? And then that would be, so the negative conjugate went down or the conjugate went up. So the idea is you can visualize it. Here's what's kind of cool. It turns out that the conjugate of any function is convex, period. Any. Looks like a deep mathematical fact or something like that. It's extremely easy to show. Let's show it. What kind of function of y is that expression? What is it? It's affine, right? I heard someone say linear. That's cool because we're among friends here, but it's affine. Okay. No, I mean, you know what I mean, right? So it's affine. Okay, so an affine function is, and this is critical because we're going to promote it to something, convex. So I can also promote it to concave, by the way. That's what it means to be affine, because you're both. I'll promote it to convex. This says take the supremum parameterized by x of a family of convex functions. In fact, they're affine. Well, the supremum of any family of convex functions is convex. So this is convex, period, right? So, okay, so that's the conjugate. Okay, some examples, you can work these out. I mean, it's a bit silly right now, but I mean, you should go through this once, but then later this will also be just a completely central part of the course. So if you take the negative logarithm, you would have to, for example, calculate what this is, and you'd work out what that was. I mean, it turns out if y is bigger than or equal to 0, the answer is, when you take the supremum, it's plus infinity. If y is negative, though, you can work out what this is. You can work out what the optimal x is, and so on and so forth, and you get that expression. Here's an interesting one. Take a convex quadratic. So that's 1/2 x transpose qx. And then you calculate the supremum of this. Well, this is easy to do. You just set the gradient equal to 0 because everything's got the right curvature. And it turns out the answer is this. So the conjugate of a quadratic form is the quadratic form with the inverse matrix, right? So there's, and we'll see there's lots of interesting things going on here. So now what we're going to do is we're going to talk about three extensions of convexity, right? So there's actually like tons, like 20 or 30 different extensions, and they have all sorts of names like quasi-convex, pseudo-convex, quasi-pseudo-convex, generalized convex, generalized quasi-pseudo-convex, and so on. And often in these books, somewhere around page 500, there's usually a diagram. So now we get a very clear picture, and that's going to be like 20 different things. And you'll say, now we see that a pseudo-convex, sure-convex, quasi-convex function is also such and such convex. Anyway, so, all right. So, some of these extensions are useful. Others, maybe not so much. So, done a bunch of triage here and come down to a handful that are actually useful, like 3. Okay? And they're fairly natural, but these are things that are going to come up all the time. So quasi-convex is one, and a function is quasi-convex. What that means is this: it says that the sublevel sets are convex. That's all it means. Oh, another name for this is unimodal. So in probability, it would be referred to as unimodal, and maybe some other fields too, right? So. And for example, for a scalar function, it just means the following. It says that if I slice the function at any level and I look at the sublevel sets, well, in R, I get an interval, but it could be half, like for example, when I slice at beta, I get a half infinite interval. I mean, I get an infinite interval, right? Everybody got this? And it's not hard to figure out what the condition for quasi-convexity is in R. It's basically that it is monotone decreasing up to some point, and then, monotone non-increasing, and then monotone non-decreasing to the right of it. That's it. And that, by the way, that justifies this idea of unimodal, right? That it can't have 2 bumps, right? That's what it can't have. Okay. So that's a quasi-convex function. Quasi-concave is the negative, and quasi-linear is both. Okay? So let's look at some examples. Well, the square root of the absolute value of x, that's a function that looks like this, right? And that is definitely not convex, and it's definitely not concave, but it's quasi-convex, right? Because sublevel sets, if you draw a level here, is just an interval, so you're okay. Here's one, the ceiling. So that's the integer part, right? Or the integer that's bigger than the given function. That's pretty weird because that thing is integer valued, right? And you don't have very many integer valued convex functions. Well, you have a couple, but they're really silly, right? Mostly they're constant, right? And not interesting, right? But that says you can be, the ceiling of a function is quasi-linear. They'll see some more other interesting examples, certainly in the book and in homeworks and things like that. Log x is quasi-linear. So it's both, a monotone function is both quasi-concave and quasi-convex. Here's one, x1, x2. That's a product. That is definitely not convex. It's not concave. In fact, it's Hessian, right? That's a quadratic form, right? And the Hessian is just this, right? It's like that. And matrices like that, it clearly has split eigenvalues, right? It's got a positive one and a negative one, and that tells you kind of like where, if you look at that function closely, well, globally, because it's actually a quadratic form, it says that in one direction, it goes like that, and in another direction, it curves up. It's a saddle point everywhere, right? That's the curvature. So that thing is for sure not convex, not concave, but it is quasi-concave. And to test that, you'd say, what are the points that look like this, right? x1, x2 is bigger than t. That's the hypo. This is not the hypograph. Sorry, this is the super level set, not the sublevel set. Oh, and of course we have to have xi positive, right? That set looks like this. That's all these things. That's all this stuff over here, right? And for any t, that's going to be convex. Okay, so that's it. There's a lot of other ones. Oh, a very famous one is linear fractional. So a ratio of 2 affine functions. Notice it's called linear fractional, but that's already ingrained in standard mathematical speech. So anyway, linear fractional functions are going to be actually quasi-linear, right? Because if you ask, what are the points where f is bigger than some value t, right, or less than some value t, all you do is you take the denominator, put it on the other side, and you get a linear inequality, so you get a half space. Everybody got that? So I just said that, but that's you'd want to check on that. Okay. Here, let's look at one that's real. So is internal rate of return. So here, a vector x represents a cash flow. And the sign is if it's cash coming in, it's positive. Okay, so it's a cash flow, right? So and then lots of things would look like you could write out all sorts of financial instruments as I guess they're non-contingent financial instruments. So you could write them out as a cash flow vector, right? Like if I lend something to someone else, then what happens is my x0 is negative, and then all my x1s, x1, x2 up to xn would be principal plus interest payments, right? An interest-only thing would look like I have x0. If I borrow interest only, x0 is positive. I then have negative things because I'm paying the interest, and then on the last step, the last one, I would pay off the principal, right? So something like that, right? And you can all of these things, right? An amortized loan, all these kind of things, right? Okay. So that's a cash flow. It's a vector. So we're going to assume x0 is negative. That means we're going to make an investment. That's cash. So on the 0th thing, we're going to invest. You can turn it around too. It doesn't matter. But we're going to invest an amount x0. And then you should interpret x1, x2, x3. Those are payments to us. I mean, if they're positive, we hope they are. Right? By the way, they might not be. There might be further investments. But if they're positive, the idea is that we make an investment of x0 and then x1, x2, x3 up to xn. That's money that comes back in. Okay. Well, if you have an interest rate R and you discount these cash flows, then this would be the present value, right? It's just the sum of 1 plus R to the minus I xi, right? Because the I is indexing periods in the future, and you discount each one by the interest rate. Okay, so that's the so-called present value, and it's a function of the cash flow vector and the rate, interest rate. Then the internal rate of return of a cash flow vector or investment sequence here is this. It's the smallest, by the way, it's not said this way because people are not clear about these things, and it's usually wrong and all that kind of stuff. But in fact, this is the correct way to say it. They say this. It's the interest rate which makes the present value 0. Okay? So that's the idea, right? So that's silly because if this thing here could actually be 0 for multiple values of R, in which case it's the smallest one, right? So it's the smallest interest rate which makes the present value 0, right? And so the idea is something like this. If you make a good investment, it means x0, you don't put in, your initial investment is not very much, and lots of stuff comes back to you. And it comes back to you so fast that even that it takes a lot of discounting to make it look like the net present value is 0, right? So that's the idea. But, okay. So this is the internal rate of return. That's really quite complicated as a function, if you think about it, right? In fact, if you really, the only way you'd be able to do this would be to do something like, to even compute this, you'd take x and you might do something where you'd try some internal rate of return and look at it, and you'd vary it or calculate the internal rate of return over 100 values or something like that. And that would give you the internal rate of return to some accuracy, right? You'd find one where it's slightly negative, one where it's slightly positive, and okay. It's a complicated function, but it turns out it's quasi-concave. So quasi-concave says this. It says the internal rate of return of a cash flow sequence, right, exceeds some number R, say 10%, right? That's true if and only if the following is true. For all discount factors up to that 10% value, right, the net present value is positive, right? So that's the idea. Okay, so that would give it to you. This, as a function of x, what is that actually geometrically? This inequality for a fixed value of R, what does that look like in cash flow space? It's what? For a fixed value of R? No, it's just polyhedron, I agree, but it's much simpler. What is it? Half space. Yeah, it's an open half space. Okay, so that's an open half space. And then this says you have to take the intersection of an infinite number of open half spaces, and you get. In fact, it turns out the answer is closed, but that's irrelevant. So you take the intersection of an infinite number of half spaces, and then that's actually going to be your super level set. And that basically is saying the interpretation of this is beautiful. It says these are the cash flow sequences which have an internal rate of return exceeding, let's say, 10%. Right? It's not all of them, of course. There's a whole bunch of crappy cash flow sequences, good ones. But the point is, it says that the super level set is convex, right? And that means this thing is quasi-concave. Now, I'm moving fast. There's no way you could get all of this right here. So the idea, more or less, here is just to get kind of the idea and the flavor of it. Okay. So let's look at some properties of quasi-convex functions. The first is you have a modified Jensen inequality. Instead of saying that f, if you evaluate it at a mixture of points, is less than the corresponding mixture of f values. Instead of that, this says you just write max. And so the picture is kind of cool. It's this, right? Here's a generic quasi-convex function, like that. And what it says, so convexity, let me take some points where it's definitely not convex. There, okay? So if I take those 2 points, that's x, right? That's y, and let me just take the midpoint. That's theta equals a half, and we can see that by Jensen's inequality, we're not doing well here. It's violated, right? Okay. However, what this says is that if I draw, it says that instead of lying, you don't have to lie. The function doesn't have to be below the chord connecting these 2 points on the graph. It has to be below this box, which is kind of goes from whatever the taller of one of them is and then down, right? So it has to sit under there. That's a quasi-convex function. There's first order conditions, and I think we'll come back to this later in the course, but it's basically something like this. It says that if f of y is less than f of x, then the gradient of f of x transpose y minus x is less than 0. So these might be the sublevel sets of a quasi-convex function, and it says that if that is the gradient, right, then it says that all points that have a lower value of f lie in this half space. Okay? So there are some things you have to worry about. Things like this. Sums of quasi-convex functions are not quasi-convex. And extreme, I'll draw the picture, and that's the end of the story. So here's the picture. There's a quasi-convex function, and here's another one. Okay? And now add them together in your head, please, and you will see a non-quasi-convex function, right? Or maybe clearer, a non-unimodal function, right? Because you'll see something that's got 2 bumps. You draw your sublevel set right at the right thing to get 2 intervals or whatever you like as the sublevel sets, and it's all over. Okay? So, okay, next generalization. This is going to be 2 out of our 3. Is log concave. Actually, the quasi-convex stuff is actually fairly straightforward. It just introduces some notation for some stuff that's obvious. We'll solve a lot of problems that are quasi-convex and things like that. We'll get to that later. Log convexity, and by the way, for some weird reason, it comes up, what's interesting always is log concavity. This is not a simple extension. There are some things here that are not obvious at all. It appears to be quite deep. So a function is log concave if its log is concave. I mean, that's what it means. Very simple. And what that means is this. Another way to say that is this. It says that if you evaluate f at a mixture of 2 points x and y, if it were concave, it would be bigger than the mixture of the f values. But here what it says is it's bigger than the geometric mixture. Weighted geometric mean, however you want to call that. Okay? So that's what it says. And you take the log of this, and that's what it means to be concave. Okay, so it's log convex if the log of the function is convex. And the functions obviously are positive. So examples would be powers. But this is actually where it really comes up. And we'll see this later in great detail. It turns out tons of common probability densities are log concave, right? So that's going to be completely, tons. In fact, it takes you a while to even think of a named distribution that is not log concave. You can, especially if you're in statistics. But generally speaking, all the ones you bump into, they are all log concave. And that's going to have huge implications later in the class when we do statistical methods and estimation and things like that. And they're going to be good. the consequences. So here's one. Here is the density of a normal random variable with mean x bar and covariance sigma. Okay, and if I take the log of that density, what do I get? Well, I get a constant. That's not relevant. Minus a convex quadratic. So it's a concave quadratic. Okay, so that's an example. By the way, a uniform distribution on a convex set, right? So any uniform distribution on any convex set has a log concave density, right? Because let's talk about what that is. If I have a uniform distribution on a set C, then the density is a constant on C, and then off of C, the density is 0. You take logs, it says the log of the log density is a constant, so log of the original constant, right, on C, and then it goes to minus infinity. And you visualize that in your head, and you realize that's concave. Okay? In fact, that's really the extended valued extension, right? So that's another one. Here's one. This is much less obvious. The cumulative distribution function of a Gaussian. Okay, so that is log concave, right? So that's something that looks like this, right? It goes like that, and so something like things with like these sigmoidal shapes. Many of these. Well, actually, the cumulative density of any log concave density is log concave, but we'll get to that, right? But when you look at that, that does not look concave, right? So what you have to do is you look at that thing and you take the log in your head, right? And when you take the log in your head, here's what happens. That's like a half, right? That's 1, and this is going down to 0. And so what the log does is over here, it takes that part of the curve and bends it down, and what you get is a quadratic. Okay, so you just get a quadratic. Sorry. You get something that approaches a quadratic, I'm sorry. So in this case. Okay, so this would give you something like that. Okay. Well, let's look at some properties of these. Well, the first is if you have one condition is this. You can say that a twice differentiable f with convex domain is log concave if and only if this inequality holds. And we can rewrite this another way. We can write it this way. I'll just erase this part. It's this inequality. Now, concave would be if the right-hand side of this expression were 0, right? If that was a 0 matrix, that would be concave function. It says the Hessian is negative semi-definite. Here, though, you allow the Hessian to be less than or equal to a rank 1 matrix, right? So you have to know a few things with what I'm about to say, but I'll say it anyway. That says you can have one eigenvalue of the Hessian can be positive, and you can still be log concave. Okay? Now, how do I know that? Well, if a matrix is less than a rank 1 matrix, then in fact all its eigenvalues but 1 are less than or equal to 0. Okay? So this is just to give you some flavor of this. So it says that more is allowed, and in fact we already saw that earlier, right? So here's an example where clearly here the second derivative is positive, but you take that log and it ends up being negative. Okay, here's one. Let's see. Product of log concave functions is log concave. That's trivial because if you take the product of two functions and take the log, this basically says that the sum of two concave functions is concave. So this is easy. The sum of log concave functions, that's not always log concave. So in probability, that means that a mixture distribution with log concave distributions is not necessarily log concave. That's totally obvious, right? Because look, here's a Gaussian, here's another Gaussian. You take the sum or the average to get the mixture distribution, and it's definitely not log concave. Okay? And then here's a very interesting one, integration. If you have a function that takes I block the argument into two things, and I integrate over one set of variables. So this is like partial minimization, but this is partial integration. Okay? If I do that, the result is log concave. Okay? So if I integrate out over, and by the way, this is part of conditioning or something like that in a dense, if you'd like to think of it that way. And what that says is this thing is log concave. The integral is log concave. We'll look at that. By the way, for that fact, I am unaware of an elementary derivation of this. So here's some consequences. It turns out that because the integral, it turns out the convolution is log concave. It's preserved from. That's very interesting for probability densities because this says the following. It says that if I have two random variables, each with a log concave probability distribution, then the sum of those random variables, also whose density is the convolution, it says that sums of. It says if you take sums of random variables with log concave distributions, you get a log concave distribution. It's preserved, right? Here's one. This is a very interesting one. This is, and this one has, this alone just has huge applications. It's this. If you have a convex set, and I have a random variable with a log concave PDF, then the following is true. I make a function which is this. This is actually called the yield function often, like in manufacturing. It says it's the probability. So I have a set that looks like this. You know, here's my set C. And what I do is to evaluate my function, I take x, and then to that I add this random variable. Okay, so it doesn't matter. Let's make it Gaussian or something. It doesn't really matter. It's some Gaussian, and it's spread around here. So it would. I'll try to draw it. I don't know how to draw a distribution, but it looks something like that, right? There's a little volcano that kind of goes up, and then the point is now you look at that as what you do is you take the total probability in the set, right? And then you move that target point x. You can think of it that way, and it changes the yield, right? So the application of this is pretty simple. C is a set of values of some parameters that are acceptable, right? So it's you build a chip or something like that, and it means that the final thing actually does clock at this rate and lasts this long or something like. It doesn't matter. It's some manufacturing problem. Everybody got it? Then Y is just the variations in manufacture. Just uncontrollable, right? Critical dimensions, things like that. Your ability to control the process and things like that. I mean, that you're pushing everything to the absolute limit, so it's not like you can. Yeah, if the distribution is super tight, then you're not doing high-end manufacturing, right? You could be pushing this way harder, right? So you push it, and it looks like that. Then the problem of choosing X is the target point that you set your manufacturing machines to do. You say, please target this. And, look, if you target it out here, that's like really dumb, right? Because basically most of the time, the thing it doesn't work at all. By the way, every now and then it works, right? Because every now and then a random manufacturing fluctuation will come up with that point, and you'll have one working device. Everybody following this, right? So this point here would not be a particularly good choice yield-wise, okay? And so then obvious question is what target point would you choose to maximize the yield, right? And it takes very little imagination to realize actually how much this would actually mean in certain contexts, right? I mean, it's incredibly important, right? And so the idea is it's going to be somewhere in the middle. What this says is that function, the log of that yield function, is actually concave. That says we'll be able to maximize it. Right, so that's going to be a convex optimization problem. It means we can effectively solve that problem, right? So just this little thing already has like serious implications. So how do you show something like that? Well, you just set it up for this integral thing, and so the way you do it is this: you write this thing, the thing we're interested in, as the following, as it's an integral of two things, the product of two things, actually, and these things are the following. So P is that's the density of Y. And G is this weird function that's like 1 or 0, right? Both of those functions are log concave, right? P by assumption. G is because G is, actually it's silly. It's log is 0 on C, and then it's minus infinity outside C. It's a silly, but it's a concave function, right? Product of two, log concave. Integral over sum of the variables, in this case just Y, that's log concave. And this is what you have. So that's the idea. Okay, so I think we already talked about this. This is the idea. And this says that the log of the yield function is concave. So, and by the way, we don't know that yet, but we'll see later. That means that basically we can effectively maximize it, right? So, by the way, a lot of weird things happen this way, where there's an asymmetry in what you want to do with something, and there's also a strong asymmetry in what you can and cannot do. This is a perfect example, right? You take a yield function, There's a strong asymmetry here. You want to maximize it. You don't want to minimize it. Well, you can turn everything around and that would be you want to the set C would be some terrible outcome, and you want to maximize. You want to avoid it. But anyway, and then it turns out it's concave. That's something we can maximize. If it were convex, we could not. So okay. And our final generalization of convex functions is to generalize it to the idea of vector values, right? So here the idea is I'll take a function which takes, as usual, a vector argument, but it returns a vector argument, not a scalar argument. So I take a vector argument, and you define a function to be k-convex if the domain is convex and if this Jensen inequality holds, but it holds with respect to this cone k. Okay? Now this mostly only comes up in a couple of, in a couple of places. I mean, a couple of these are come up much more often than other things. And so one, for example, if this is matrix inequalities, and if these are symmetric matrices, and that's matrix inequality, then a function that is k-convex with respect to the positive semi-definite cone, that's called matrix convex. So that's so here, for example, if I have a mapping from m by m symmetric matrices into m by m symmetric matrices, and the mapping is the following: you square the matrix, that's it. Then the claim is that is convex, matrix convex. Okay, and what you have to check is this: you want to check here whether or not you have to check whether z transpose x squared z is convex with respect to capital X, right? For each z. That's what you have to check. And that is true because you write it this way. And now this expression, capital X times little z, is actually linear in capital X. And then you have a norm squared, that's convex. Okay, so this expression is convex in capital X. Okay, by the way, kind of suggests that, right? I mean, if x squared is your canonical convex function, little x squared, then why wouldn't capital X squared be convex as well? By the way, you have to be very careful with these things because some things are wrong. For example, exp, you don't get a whole lot more. I mean, that's convex, and the exp of a matrix, symmetric matrix, is actually not matrix convex. So there's some weird stuff happens. I mean, seriously weird stuff. But in this case, it didn't happen. Okay, now this is true for any z, and that tells you that I remove the z's and I change this inequality to a matrix inequality, because that's what it means for matrix inequality to hold, right? It says that if you take the one quadratic form and another, this quadratic form is always less than this one. If that's always true, then it means that this matrix is less than or equal to this one in the matrix sense. And so you get a statement that looks like that. Okay? So that's it. And it's a sophisticated statement.